Hello. In this video, we'll be understanding the Chinese remainder theorem. We'll go through the proof, the algorithm, and I've also prepared a practice problem at the end. So I have included in the description the sources I found helpful, and I also made my own summary of CRT, so you should check that out too. But before we begin, recall that the prerequisites for understanding CRT are modular inverses and a basic knowledge of modular arithmetic. So I also included links for those in the description. Okay, so we are given k positive integers. So we have a sequence of integers, m1, m2, until mk. Okay, so they are all positive. And they are pairwise coprime. So whichever pair you choose, so whichever two different elements, mi and mj, you choose, their greatest common divisor is equal to 1. They're coprime. So you have another, you are also given another sequence of integers, which are a1, a2, till ak, okay? These are going to act as our remainders here. Now, CRT states that given this system of congruences, this one, we're going to solve for x. There is a unique solution taken modulo m being the product of mi. So like m1 multiplied by m2 until mk. So this is a multiplication. Now, you should always remember the condition here is that the moduli, which is the sequence mi, they are all pairwise coprime. Okay, that's the important condition. We're going to see at the end a more general CRT where there are non-coprime moduli. Okay, all right. So what we mean here by a unique solution taken modulo m, meaning that there are infinite solutions actually. If you look at the integers, there are infinite integer solutions. However, if you only take this range, which is from 0, this integer range from 0 to m minus 1, you will find one unique solution that we can call like x0, I guess, which is going to be in this range. And the other solutions will be of the form x0 plus some integer q times m. Let's start by finding a solution. For that, we will define a sequence of integers, yi, which is going to be equal to m over mi. So essentially, don't forget this is the product of the sequence m. Okay. So essentially, it's going to be like the product from m1, m2 until mi minus 1. Then we're going to skip mi, and we're just going to go from I plus 1, mi plus 1, until mk. Okay, so it's like the product, but except mi. Okay. Now, we're also going to define another sequence, which is going to be yi to the minus 1. This does not mean this. It's not mean that. That's not the inverse. That means it's the inverse. It's the modular inverse. So it's the inverse of yi modulo mi. Okay. So let's recall what a modular inverse is. So let's say we've got two integers, x and m. M is going to be our modulus, and x is some integer. So we have a condition here. It's that x and m must be coprime. So their greatest common divisor is 1. That's the condition. If so, there exists a certain integer, which we will note as x to the minus 1, such that x multiplied by x to the minus 1 is congruent to 1 modulo m. Okay? So it's essentially like division for modular arithmetic, but it's not really division because we don't do that in modular arithmetic. Right? So again, if you want more about this in detail, I've put a great link in the description about modular inverses. You should really check that out. So in this case, remember we set a condition here for the inverse to exist, yi must be coprime with mi, and indeed it is, because remember, mi are pairwise coprime, so they do not share any common factors, and yi is stripped from mi, so it makes sense that yi and mi are coprime. So indeed there exists a modular inverse. So now we're going to define our solution. Let's call it x0. It's going to be equal to the sum from I equal to 1, that's okay, of ai times yi to the power of to the minus 1. It's not really a power. Again, yi is the sequence we defined, and yi to the minus 1 is the corresponding modular inverse. Let's check for the solution now. So remember, if x is a solution, then x must satisfy x congruent to ai modulo mi for all I. Okay, so we're gonna take some random I. So for some I, we have x0 is congruent to, remember x0 is the sum that we wrote here, so it's going to be equal to a1 minus 1 plus a2 to the minus 1 plus that goes until ak to the minus 1, all modulo mi. Okay, so now remember, if one of these terms is divisible by mi, then we can just remove it or replace it by 0, because it is going to be congruent to 0 modulo mi. Okay, and if you remember, yi is equal to the product of all the integers in the sequence m except mi. So all of these terms are going to be divisible by mi, because they're going to have mi, except the one which has yi, which is ayi times yi to the power of minus 1, to the minus 1. Okay, so that's the only one that's gonna stay. All right. Now, if you recall from the definition of a modular inverse, if it exists, then yi times yi minus 1 is congruent to 1. Okay, so this we can replace with just 1. So in the end, only ai remains. Okay, and we have determined that x0 is indeed a solution. Let's now prove the uniqueness of the solution. Again, not in the integer set, but in the range 0 to m minus 1. So modulo m. That's where we're going to prove the uniqueness. All right. So a good place to start from is to suppose we have two solutions that satisfy our system. Let's call them u and v. This means that for every I, we have u congruent to ai modulo mi and v congruent to ai modulo mi. Right? This means they have the same remainder. So u is congruent to v modulo mi. Makes sense, right? So let's bring v here, so it becomes u minus v congruent to 0 modulo mi, which means mi divides u minus v. All right. Now, let's suppose you've got a divides x, right? Forget our old variables. Suppose you've got a divides x and b also divides x, right? Now, if a and b are coprime, so their greatest common divisor is 1, then that means a times b divides x. Okay, that makes sense, right? Because they don't have any common factors. So since this works for all mi, and all mi are pairwise coprime, so whichever pair of mi you take, they're always going to be coprime. We can then deduce that m, the product of all mi, divides u minus v. Okay, which then means that u minus v is congruent to 0 modulo m. Okay, so let's bring v here, then u is congruent to v. So essentially, they have the same remainder modulo m, these random two solutions we chose, which means they are the same solution taken modulo m. So we've proved the uniqueness now. Okay, now before we move on to the algorithm, while researching for Euler's Totient function, I had to go through CRT, of course, and I've had this question, and answering it helped me understand. Helped make my understanding more satisfying. Helped me understand the Euler's Totient function more, which is probably going to be our next video. Okay. So imagine you have two systems of congruencies, which has the same number of congruencies, k. So they have the same moduli sequence. So they have the same m. Okay, so m1 is equal to m1 here, and so on. However, they have different remainder sequences. So S1 has remainder sequence A, which is different than remainder sequence A prime of S2. This means that there exists a certain index I, such that AI is different than AI prime. At least one of them is different. Okay. Now my question is that what if there exists a certain solution, x0, a certain integer, that is in the range 0 to m minus 1. Okay, remember they have the same modulus m, because they have the same sequence of moduli. Alright, so what if this is not just the solution of one of these systems, but both of them? So like solution of S1 and S2. Okay. Now, this yields x0 is congruent to AI modulo mi, and x0 is congruent to AI prime modulo mi. Okay. Now, this means that AI is congruent to AI prime because they are congruent to the same integers as x0, which means they have the same integer. Now, remember that AI and AI prime are remainders, so they both are in this integer range. So mi minus 1. Okay, they're between 0 and mi minus 1. Which means this actually means that they are equal, which contradicts this right here. Okay, so our initial supposition is false. So x0 cannot be simultaneously a solution for like two systems that have different combinations of remainders, but the same moduli. This in turn means that we have a sort of bijection here. Okay, so let's say you've got a set of all the possible combinations of the remainders of different combinations of a1, a2, ak. Okay, so let's call them like a1, a2 until am. Okay, so how many combinations are there? If we take a1 can take values, integer values from 0 to m1 minus 1, right? So in total m1 possibilities. Same goes for a2. There are going to be m2 possibilities, and so on. So in the end, like the total number of combinations are m1 times m2 times till mk, which is going to be equal to m. That's why I put m here. So the cardinality of the set is m. And now let's write the possible solutions here, which are going to be 0, 1 until m minus 1. So again, same cardinality, m. Now, imagine these combinations as the possible systems that we're going to have. So all of the systems will have the same fixed moduli, okay? But each system will have a remainder sequence AI, okay? And each system will have a unique solution, right? Because remember, this is the range 0 to m-1. So there's going to be a unique solution in this set right here. And we just proved that that one solution cannot be the solution of two systems. So this cannot happen. So that means there's a bijection here. Okay. Now you don't necessarily need this for CRT, but it was very useful for me for understanding the intuition behind the properties of Euler's Totient function. Okay, so here's the algorithm. It's not really that complicated. So first we have a struct here of congruencies. Okay. Now each instance of this struct actually just means that X is congruent to A mod M. Okay, that's it. So we're going to have, in our case, K instances of struct, and they will be passed as an argument in a vector to this function. Okay. Now first we calculate M, which is the product of the sequence M. Now we define our solution. Now we go through all these congruencies and we calculate all the terms one by one. Okay. So and then we add to the solution. We just keep adding to the solution each term, and we always take it modulo M in each step. This is so that we can avoid the overflow. Very standard procedure. Okay. Now about the modular inverse here, this function up here. Now, if you recall, mi and yi must be coprime, right? So there are multiple ways of calculating the modular inverse, but in this case, we should go with the extended Euclidean algorithm because it's the more general one. If you use Fermat's little theorem, it only works if mi is prime, and that is not always the case. Okay. If you want more info about this, always check cpalgorithms.com. It's a really good site. Again, I've included links in the description. Okay. And now we're going to work through an example here. Now here's the example. So I've got 3 moduli, 3, 5, and 7. They are 3 distinct primes, so obviously they are pairwise coprime. So there exists a solution. Let's calculate M first of all. It's 3 times 5 times 7 is 105. And then let's calculate the sequence Y, where yi is equal to M divided by mi. So first we've got 5 times 7, it's 35, and 3 times 7, that's 21. And 3 times 5, that's 15. Now, to calculate the sequence of the modular inverses, we should use the extended Euclidean algorithm, but I'm not going to do that manually, so jump back to VS Code and do that here. So, need the modular inverse first of 35, 33. And oops. This is going to be 21. Yeah. Right, no, this one is 3. This one is 5. This one is 7. Yeah, it's good. It's good. Okay, and now this one is recall 15. Okay. Yeah, 2 and 1 and 1. Okay. 2 and 1 and 1. Now, if we calculate the sum to 3, k is equal to 3. So if ai, yi, this one, that's going to be equal to 2 times 35 times 2 plus 21 times 10 times 3 plus 15 times 2. Okay. So that is this is 70, 140 plus 63, I guess, plus 30. Okay. This is 203, so it's equal to 233. Now we found the solution, but now we want to find the one which is in the integer range 0 to 105. So I think we just need to remove 1 to 105. So it's like 210. 233 minus 210, that is 23. Okay. Now let's just run the algorithm to check our solution. Oops. So let's create our vector congruencies. Let's call it V. It's going to be equal to let me do this. Just this. Called 2, 3, 3, 5, 2, 7. 5, 7. Okay. I guess that works. Now let's just do Chinese remainder theorem. That's our congruence. Another remainder. I mean result. Let's see our result. Oops, what happened? Oh, yeah, of course. Yep, 23. Alright, so our solution is correct. And the rest of the solutions here are going to be of the form 23 plus q some integer times m, which is 105. Okay. Okay, now finally, before we move on to the practice problem, we will go through one more very important section. We will go through a more general CRT. In this case, the moduli are not necessarily coprime. So there exists two certain distinct indices, so I is different than j. And mi and mj are not coprime. Okay? So our initial moduli sequence is not pairwise coprime. So let's say for some I, we have mi is equal to p1 and q, p2 to the, this is n1, this is n2, until pq to the nq, okay? This is thanks to the fundamental theorem of arithmetic. So p1 and p2 until pq, they're all distinct primes, and ni are like the highest powers, okay? So this means that if we have x congruent to ai modulo mi, this is equivalent to this system of equations. So like x is congruent to ai modulo p1 to the power of n1, and x congruent to I mod p2 to the n2, so on until pq to the nq, okay? Now this makes sense because going from here is easy, because if you've got x is congruent to, let's say, y modulo a, and B divides A, meaning A can be written of the form B times Q. Okay, this means that X is also congruent to Y modulo B. Makes sense, right? Because don't forget, congruence means X equals Y plus A times a certain integer K. So like if right here A is equal to B times Q, we can change this to Y modulo B. Okay. So in this case, going from here to here, obviously all of these prime factors divide mi. So this implies each one of these. That makes sense, right? But going from here to here now, it also makes sense because all of these are pairwise coprime. And we know that if X is congruent to, let's say, A modulo, I don't know, M, and X congruent to B, I mean, yeah, A modulo N, and M and N are like coprime, so their greatest common divisor is 1. That means that X is congruent to A modulo M times M. Okay, so we're just, since these are all pairwise coprime, we're just going to multiply all of them, and we will end up with X congruent to AI, which is the common remainder here, modulo the product of these, which is mi. Okay, so if we take like an example here, which is 60 is equal to 2 to the power of 2 squared times 3 times 5, right? So if X is congruent to a certain A modulo 60, this is equivalent to these three congruencies. So X congruent to A modulo 2 squared, and X congruent to A modulo 3, and same thing for 5. Okay. Essentially, what this means is that we can transform our original system into a system with only congruencies modulo prime powers. So what we can do is we can go through each of the original congruencies and replace them with their corresponding equivalent prime power congruencies, as we did with 60 here. So I prepared an example here. So let's do just that. So for the first modulus here, 8, it's already a singular prime power. Same goes to 9. 3 squared. 12, that's 2 squared times 3. Okay. So for the first two, it's simple. Modulo 2 to the 3. I like this instead of 8 for more clarity. And X congruent to 4. Modulo 3 squared. And now 12 is going to give us 2 congruencies here. So 1, always same remainder. Modulo 2 squared and modulo 3. Okay. Now that was the first step. Now I want you to consider congruencies based on the same prime. So for example, if it's 2, then we will consider these ones. And if it's 3, we will consider these 2. Okay. Now, the one having the highest power is the strongest because it implies the rest of the congruencies. And I'm talking about the one in the same group. So either the ones in red or the ones in purple. Okay. So what this means is, let's say you've got 2 powers, A and B. Let's say A is superior or equal to B. Obviously, this means P to the B divides P to the A, right? So if we have X congruent to let's say, I don't know, Y modulo P to the A, this implies that X is congruent to Y modulo P to the B. Okay, so it implies, so this means that we can just leave the one with the highest power. So the rest are redundant. So in this case, we're going to remove this one. And in this case, we're going to remove this one. So we are left with actually less than what we have originally. We only 2 congruencies. However, you should note that in the case where moduli are not necessarily pairwise coprime, there can be contradictions. So we have to check that indeed the strongest congruencies actually imply the weaker ones. So for example, if we take the case of the prime being 3, the stronger congruence here is x congruent to 4 modulo 3 squared. This implies that x is congruent to 4 modulo 3, right? Because 3 divides 3 squared. And that means if we take the remainder now, it's going to be 1 modulo 3, which checks out, which is true, because we have it as a congruence here. All right, so indeed, the stronger congruence imply the weaker ones here. And in this case, we have only 2. Sometimes we may have even more, okay? So you got to do that for all the weaker ones. Now, if we take the other case we have here, which is the prime being 2, we don't need to do anything crazy, because the first one means here that x is even, right? And the second one means that x is odd. X cannot be even and odd at the same time. So this is a contradiction. In case of a contradiction, this means the system has no solutions, okay? So that's the second step. You gotta check for contradictions. Okay, so now let me change that. Let me change this. 1 here. Change the LaTeX as well. 1 here. Now, our system actually has solutions, and we can now safely remove the weaker ones. Good. Okay. After making sure there are no contradictions now, you can notice that the moduli are actually pairwise coprime now. Like our new moduli, because they're all the highest prime powers of distinct primes. So of course they are pairwise coprime, right? And now we can just do the same things we mentioned in the video before. Now the solution is again unique when taken modulo m, but not equal to the product of mi. Okay, because remember, mi are the original sequence of moduli, which are not pairwise coprime. Instead, it is equal to LCM of m1, m2, and so on until mk. All right, that makes sense, right? Because when calculating the LCM of multiple integers, what we do is we go over all existing prime powers in either integers and leave only the factor with the highest power, right? And that's precisely what we did here with the congruencies. And that is why it is equal to the LCM. So to recap here, the first step you gotta do is you gotta convert your system into a system of only congruencies modulo prime powers. And then you have to check for contradictions. And finally, you can just redo the same standard procedure we described in the rest of the video. All right, now for the practice problem, I chose this old code forces problem, which is not bad. It's rated 1800. It's called Remainder's Game. By today's standard, it's probably 1700. Since old problems are a little overrated. So we got 2 characters here, Pari and Arya. I'm gonna call Arya a she. I don't know what she is, but whatever. Just for simplicity. So Pari chooses 2 positive integers x and k, and tells Arya k but not x. Alright, so Arya has access to k, and so do we. We also get k in the input. Arya has to find the value of x mod k, not x itself, but x mod k. Okay, so the remainder of x, modulo k. There are n ancient numbers, so we get a sequence of integers, ci, and Pari has to tell Arya x mod ci if Arya wants. So Arya also has access to another sequence, which is AI modulo CI. Okay. So this goes for AM. Okay, so she has access to these as well. All right, but we don't. We only have access. All right, so look, we are only given k and the ancient values, these. All right, we are not tasked with finding x. We need to only say if Arya has a winning strategy independent of value x or not. So can she figure out the value of x mod k, knowing only this information right here? So we will output yes or no. Okay, so this already looks pretty familiar, right? Right here. This is actually the a case of general CRT, because it does not say up here that the moduli are necessarily pairwise coprime. Okay, so in fact, like look at this 2 and 12, they are not coprime. They're both divisible by 2. Okay, so this is equivalent. This system is equivalent to this. So x congruent to, let's call this x0 modulo LCM of C1, C2, and so on until Cn. Okay, let's call this value L for simplicity. And we want to know if she can find x. You can find y, such that y is the remainder of x modulo k. So x mod k. Can she find that from this? Now, when does this imply this? Now, obviously here we got the same x, right? So of course, we've already mentioned this a lot of times in the video, but L must be divisible by k. Okay, so L must be either k, 2k, 3k, and so on. All right. So that's the only condition. It's not that hard once you study CRT. All right, let's move on to the solution now. So let's back to VS Code. Do not go straight into implementing, because as you can see, we do not need the implementation of CRT, but we do need to understand it. Okay, so let's delete that. We do not need it. However, what we do need is the function GCD and LCM. Right, so I'm gonna take those back here and paste them. Okay. Now let's go through our inputs. Okay. Next step is we gotta calculate the LCM, because we gotta check if it's divisible by k or not. For that, we'll go through, iterate through the values of CI. Okay. Now L is equal to LCM, L, and CI. Yeah. Okay. Now we check if L mod k is equal to 0 or not. Yes, else no. Alright. Let's run the sample test cases. Passed. Now, you gotta always check your constraints. So one thing here is that CI can reach 10 to the power of 6. So it can get quite big. And LCM can grow exponentially, so like very fast. Okay, so we have overflow problems here. But if you recall, we were trying to find if L is divisible by k. So we only need to keep track of the factors of k. We do not care about the other factors of L. All right. So to do that, we can just apply GCD on this and k. Okay, so GCD of the value of L and K pretty much in each step filters the factors we do not want and only keeps at max the factors of K, right? So and also this means that L in the end, if it's correct, if the answer is yes, then L must be equal to K. Okay, so we do not have the option of 2K, 3K, 4K, and so on. No. It must be equal to L. Okay, so if you run again, it's correct, and that's it. That's the video for you. I hope you understood. So I made this video with Euler's Totient function in mind. So we'll probably expect a follow-up in the future.